Turbulence emergence. Chaos from order. Water moving smoothly from a tap can shift into a churning, unpredictable pattern once the flow is pushed harder. Physicists describe the first state as laminar flow and the second as turbulent flow, and both can be modeled with considerable accuracy. Weather forecasting, aircraft design, and blood flow through the body all depend on understanding how fluids behave. No mathematical proof exists for the exact point where smooth flow becomes chaotic. The transition can be observed in a wind tunnel and reproduced on a supercomputer, but no formula defines the precise threshold where order ends and turbulence begins. Some physicists attribute this to computational limits, expecting that greater processing power will eventually locate the threshold. Others argue the transition may not have a fixed mathematical boundary at all. There may be no clean line between order and chaos in the first place, only a blur that can be simulated, but never precisely defined. The cosmological constant, a 120 order discrepancy. Empty space is not without energy. Quantum field theory holds that a vacuum still carries measurable energy from constant fluctuations. Physicists can calculate the predicted value of that energy, but comparing it to observation reveals a difference of roughly 10 to the power of 120. This is not a minor discrepancy. If the same margin of error applied to an estimate of the number of atoms in the observable universe, the result would fall far outside any reasonable range. This is widely regarded as the largest gap between theoretical prediction and experimental observation in physics. Quantum mechanics and general relativity are each independently well supported, yet applying both to the vacuum produces this contradiction. Some physicists propose that an undiscovered symmetry cancels most of the predicted energy. Others expect the explanation to come from a future theory of gravity. A smaller group considers the current method of calculating vacuum energy fundamentally flawed. Two of the most successful theories in physics, each correct on their own, produce the largest error ever calculated the moment they're asked to agree. The arrow of time. Newton's laws function identically whether time is modeled forward or backward. Maxwell's equations for electricity and magnetism behave the same way. Yet physical processes are not observed running in reverse. Broken glass does not reassemble, and smoke does not return to its source. Physicists attribute this to entropy. Disordered states vastly outnumber ordered ones. So systems tend toward disorder because there are more configurations available for disorder than for order. This explains the observed direction of change, but does not explain why the universe began in a highly ordered, low-entropy state with only one direction available to it. Proving how a one-directional flow of time arises from laws that are indifferent to direction remains unresolved. Each particle, considered on its own, is blind to which way time runs. Only when enough of them come together does the universe insist on a single direction, one physics still can't fully account for. Singularities in general relativity. At the center of a black hole, Einstein's equations predict infinite density compressed into zero volume. In mathematics, division by zero is treated as undefined. In physics, that undefined outcome appears as a singularity inside a black hole. The behavior outside a black hole, including its effect on light and time, can be calculated with precision. At the center, the equations stop producing meaningful results. Physicists generally attribute this to a gap in current theory, expecting that a future model combining quantum mechanics and gravity would replace the infinite point with a finite, calculable one. Others consider the singularity a genuine limit of physical law rather than a gap in current understanding. Somewhere in the universe, there may be a place where physics itself has no answer. The measurement problem. Schrödinger's equation describes how a quantum system evolves over time as a set of overlapping possibilities, a particle existing in multiple states at once until an observation occurs. At the moment of measurement, that set of possibilities resolves into a single, definite outcome. Physics has an accurate description of the system before measurement and after measurement, but no equation describes the mechanism of the transition between the two. Some physicists propose the existence of hidden variables, an undetected layer of information that would account for the transition deterministically. Others propose that every possible outcome continues to exist in separate, unobserved branches, an approach known as the many-worlds interpretation. A smaller group has considered whether observation itself, including the role of a conscious observer, plays a part in the process. Physics has an exact description of reality on either side of that moment, and a gap in its own instructions at the precise instant reality is decided. The many-body problem. Two orbiting bodies can be described with an exact mathematical solution. Adding a third body removes that possibility. The system becomes generally unsolvable in closed form, and results depend on approximation and simulation. In quantum mechanics, calculating the exact state of more than a few dozen interacting particles becomes computationally intractable using current methods, since the number of variables increases faster than available computing power can track. Two-body systems can be solved exactly. Three-body systems cannot. Ordinary matter is composed of particles numbering in the billions. Some physicists treat approximation and computing power as the practical solution going forward. Others regard this as evidence of a genuine mathematical limit on exact prediction as system complexity increases. The universe runs on trillions of interacting parts at once, and current mathematics can barely handle 3. The Yang-Mills mass gap. The force holding particles together inside an atomic nucleus is carried by gluons, which are considered massless in theory. The force these gluons carry nonetheless produces particles with measurable mass, a discrepancy referred to as the mass gap. This mass gap has been used and confirmed experimentally in particle accelerators for decades. No rigorous mathematical proof explains why it must exist. It is listed among the 7 Millennium Prize problems, a set of unsolved mathematics problems, each carrying a $1 million reward for a verified solution. Some researchers believe a proof will require new mathematical frameworks not yet developed. Others expect existing advances in quantum field theory to resolve it. Physics built mass out of a theory made entirely of massless parts, and still can't prove why those parts agreed to cooperate. Number 1. The Navier-Stokes smoothness problem. The turbulence wall. Every time you board a plane, check tomorrow's forecast, or watch water swirl down a drain, you're relying on the Navier-Stokes equations, the mathematical backbone describing how fluids move. They're used constantly, trusted completely, embedded in nearly every piece of engineering that touches air or water. But there's a question sitting underneath all of that trust that nobody has ever answered. In 3 dimensions, no one has proven that a fluid starting out perfectly smooth will always stay smooth. Mathematically, nothing rules out the possibility of a singularity, a point of infinite energy, suddenly appearing out of nowhere, in finite time, for no obvious reason. It sounds abstract until you realize this is the exact same math holding your airplane in the sky. Like the mass gap, it's a Millennium Prize problem, $1 million unclaimed for over 2 decades, because nobody can prove these equations behave the way we assume they do. Some mathematicians believe a full smoothness proof is within reach, given more advanced tools. Others suspect blowup is mathematically real, an actual possibility hiding somewhere in the equations, simply waiting for the right conditions to appear. We trust this math with our lives every single day, in the air, on the road, in every weather report we plan around. And after all that trust, all that use, all that reliance, we still don't actually know, with mathematical certainty, whether it's telling us the truth